Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Our question wants us to consider the fact that a uniform bar with a length of 0.2 meters and a mass of 0.7 kilograms, let me write the units there, is first sitting horizontally, and then it falls to its in its vertical position, it first starts vertically and it falls and ends up in its horizontal position, striking the point A. It's attached to a spring, and the spring's initially unstrained and has a spring constant of K, and we want to figure out the tangential speed at which it strikes that surface. Well, first of all, tangential speed, V, is equal to the radius of rotation multiplied by the angular frequency omega. But the radius of rotation for us is the length of the rod L, and the omega would be the angular frequency. So we need to find omega. If we know omega, then we can calculate this value. Another value that I include is h. This is the fall height. So the height of the falling rod is going to be the center of mass of that rod. So it's going to be L over 2 because it starts vertically, and so it falls the center of mass of the rod falls a distance of L over 2 or 0.1 meters. The reason this is important is because we're going to use conservation of energy. So initially, all the energy is due to gravity. So the potential energy due to gravity in the initial position is going to be equal to, in the end, we have potential energy due to the spring, but we also have kinetic energy from the falling object, which is rotational kinetic energy, since it's falling about a pivot point. So we can call it Ke rot for rotational. Well, the potential energy due to gravity, so we can just rewrite this equation, is mgh. The potential energy due to the spring is 1/2 kx squared, where x is the amount of compression that the spring has. And the rotational kinetic energy is 1/2 I omega squared. Okay, so there's the omega value that we need to solve for to calculate tangential velocity. So the question is, what is x and what is I? Well, from Pythagorean theorem, we can determine that x is going to be equal to the hypotenuse minus half the distance of the rod. So it would be minus 0.1. Well, the hypotenuse is equal to the square root of 0.1 squared plus 0.2 squared. So the original height of the rod, center of mass, or the height to get to the spring, both are the same, plus the length of the rod. And then we need to subtract from this value the amount of half the distance to the center of mass of the rod, or 0.1. So this comes out to equal 0.124. And this would, of course, be in units of meters. I, the moment of inertia, since it's a rigid rod falling about a pivot point, the moment of inertia for a rigid rod falling about the pivot point is 1/3 times the mass. And if the pivot point is on the end of the rod, not in the center of mass of the rod, it's going to be 1/3 m times the length of the rod, L squared. Well, this comes out to equal 0.01. Okay. So now that we have a value for the moment of inertia and a value for x, we can rearrange to solve for omega. We find that omega here is equal to 2 over I, 2 over the moment of inertia, multiplied by mgh minus 1/2 kx squared. And since omega is squared, this all falls under the square root. Plugging these values in, we find a value for omega of 10.431 radians per second. Now that we have a value of omega, we can go back and calculate our tangential velocity, since it's just L, the length of the rod, times omega. Plugging these values in, we find that the tangential velocity is 2.08 meters per second. We can box that in as our solution to the question.